the grand narrative of physics. It's really a story of unification, of bringing ideas together.
Oh, absolutely. It's a series of these just breathtaking moments of synthesis.
Right. You have Newton, and he realizes that the force making an apple fall is the exact same one keeping the moon in orbit. One set of laws for heaven and earth.
Then Maxwell comes along and sweeps up electricity and magnetism, two things that seem totally separate, into this single beautiful thing, electromagnetism.
And then, of course, the big one, Einstein. He merges space and time into space-time, this single dynamic fabric. These were moments that made the universe seem understandable, rational even.
But then you get to the late 20th century, and the story changes completely. It becomes a story of conflict.
A deep, fundamental conflict, because modern physics, as you know, is built on two pillars. On one hand, you have general relativity.
Einstein's theory. It governs gravity, space-time, the cosmos. The very, very large.
And on the other, you have quantum mechanics, the rules for matter, energy, probability, the very, very small. And for decades, they worked perfectly fine, just, in their own separate domains.
Until they didn't. Until they were forced to meet.
And they met on this one single, unavoidable battlefield, a place where immense gravity crushes matter to an infinitely small point.
The black hole.
Exactly. And the intellectual conflict that erupted there became known among physicists as the Black Hole War.
And it really was a war. It lasted more than 3 decades, and it got incredibly personal. You had these titans of physics drawing their battle lines.
You had Stephen Hawking, the great relativist, who trusted the geometry of space-time above all else. He was initially allied with Kip Thorne, another giant in the field.
And on the other side, you had the quantum champion, Leonard Susskind, who basically launched a crusade to, as he put it, make the world safe for quantum mechanics.
And the stakes here, the reason this matters so much for you to understand, weren't just about some esoteric detail. The law under threat was the conservation of information.
Which is maybe the most fundamental principle in all of science.
Right. If a black hole can swallow something and completely erase its history, truly delete the information from the universe, then everything changes. The universe becomes fundamentally unpredictable. The past can no longer be reconstructed from the present.
And if that's true, the entire mathematical bedrock of quantum mechanics just shatters. It's a crisis that strikes at the very soul of physics.
So that's our mission for this deep dive. We're going to unpack this entire scientific saga. We'll start with the paradox itself, look at the famous bet that formalized the war, and then explore the wild, almost sci-fi ideas that came out of it.
Ideas like, the possibility that our entire 3D universe is actually just a hologram.
It's a wild ride. So let's start at the beginning. The core principle under attack, information conservation.
Right. To really feel the weight of this crisis, you have to appreciate just how sacred this idea is. Leonard Susskind even called it the minus first law of physics.
The minus first law, meaning it comes before everything else, before even the laws of thermodynamics.
It's more fundamental. Think about it even in a classical sense. If you knew the exact position and momentum of every particle in a room right now, you could, in principle, run the clock backwards and know where they all were yesterday.
Or run it forwards and predict the future perfectly. The movie of the universe is reversible.
Exactly. If you shatter a wine glass, all the information about the original glass is still there. It's just, scrambled in the motion and position of all the little shards. Nothing is truly lost.
Okay, and quantum mechanics takes this idea and makes it even more rigid.
It enshrines it in a mathematical principle called unitarity. Unitarity is the quantum version of information conservation, and it is non-negotiable.
So what does unitary actually mean in practical terms?
It means that the evolution of a quantum system over time, as described by the Schrödinger equation, is perfectly reversible. But it also means something deeper. It preserves the, let's call it the purity of the quantum state. A system can be in what's called a pure state. Think of it as a state of perfect knowledge. Zero entropy. We know exactly what it is. A single specific quantum identity.
Okay.
It can also be in a mixed state. That's a state of uncertainty. It's a statistical mess, like a cloud of hot, random gas. It has high entropy. The information is all jumbled up.
I see.
Unitarity demands that a pure state can never, ever evolve into a mixed state. If it does, that's not scrambling. That's true destruction. The information is gone, and the link between past and future is broken. Quantum physics collapses.
And that's the law, the bedrock. Now let's bring in the black hole, because before the 1970s, they were seen as these perfect, simple objects.
Almost boring from a certain point of view.
Yeah.
They were described by the no-hair theorem.
The no-hair theorem.
It says that once a black hole settles down, it's defined by only three things. Just three. Its mass, its electric charge, and its angular momentum, or spin. That's it.
So all the other details of whatever collapsed to form it. Was it a star made of hydrogen? A star made of iron? A giant pile of encyclopedias? All that intricate hair is gone.
Radiated away or swallowed. The final object is just terrifyingly simple, so you can see the problem already. If you can make identical black holes from completely different starting materials, where did all that information go?
That's already a huge red flag. But the real crisis started to brew in 1972 with a graduate student named Jacob Bekenstein.
Yes, Bekenstein. He pointed out a glaring problem with this simple, featureless picture of black holes. A problem with thermodynamics.
The second law of thermodynamics, specifically.
The second law. The total entropy or disorder of the universe can never decrease. But if black holes have zero entropy, as classical relativity suggested, you could break that law easily.
How so?
Just, take a box of hot gas, very high entropy,
Wrong.
lots of disorder, and just throw it into a black hole.
Poof! The gas and all its entropy vanished from the universe. The total entropy of the cosmos just went down. A clear violation.
Precisely. So to save the second law, Bekenstein made a radical proposal. He said the black hole itself must have entropy, and that entropy must increase by at least as much as the entropy you threw in.
So black holes aren't these perfect zero entropy objects, they're thermodynamic objects.
And here's the stroke of genius. He said, well, what defines a black hole? The no-hair theorem says only its geometry. So the entropy must be related to its geometry, and the most obvious geometrical property is the surface area of its event horizon.
So he proposed that a black hole's entropy is proportional to its area, not its volume, its area. That's a huge leap connecting geometry to information theory.
It was staggering, but Stephen Hawking hated the idea.
Why? It seems elegant.
Because if something has entropy, it must have a temperature. And if something has a temperature, it has to radiate heat. But a black hole, by definition, is an object that nothing can escape from. Not even light. It was a classical contradiction.
So Hawking sets out to prove Bekenstein wrong using the machinery of quantum mechanics.
He did. He wanted to deliver the final nail in the coffin for this black hole entropy idea. And in 1974, he published his results. And in a stunning twist of scientific history, he ended up proving Bekenstein was right. But he did it in a way that unleashed a far deeper paradox.
This is the discovery of Hawking radiation.
Yes. The mechanism he found is one of the most beautiful and terrifying ideas in modern physics. It comes from the quantum nature of empty space.
The idea that the vacuum isn't really empty?
Not at all. It's fizzing with what are called virtual particles. Particle-antiparticle pairs that pop into existence for a fraction of a second, then annihilate each other and disappear.
A constant quantum foam.
Exactly. Now, imagine one of these pairs pops into existence right at the edge of a black hole's event horizon. The tidal forces, the gravitational pull, is so extreme that it can rip the pair apart before they can annihilate.
So one gets pulled in?
And the other one escapes. It flies off into space. To an observer far away, it looks like the black hole is glowing. It's emitting radiation.
And to conserve energy, the particle that falls in has to have, what, negative energy?
That's the only way to balance the books. The black hole absorbs a particle with negative energy, which means its total mass goes down. It shrinks.
So black holes aren't internal. They radiate, they lose mass, and over immense, truly cosmic timescale.
They evaporate completely. They disappear in a final puff of radiation.
And this right here is the casus belli, the cause of the war. Because what kind of radiation is it?
Hawking's calculation was crystal clear. It's purely thermal radiation. Random, featureless heat, like the glow from a hot piece of coal. The temperature depends only on the black hole's mass and nothing else.
Okay, let's walk through the classic thought experiment here, because this is where the paradox becomes unavoidable.
Let's do it. Imagine we create two black holes. They are perfectly identical in mass, charge, and spin.
But we make them from totally different things. Black hole A we make by collapsing a star made of pure neutrons, a very specific pure quantum state.
Okay, and black hole B we make by collapsing, say, the entire Library of Congress, every book, every piece of information, a completely different, but also pure quantum state.
According to the no-hair theorem, once they settle, these two black holes are indistinguishable from the outside. The information neutrons versus books is trapped inside.
Now, they both start to evaporate, they both emit Hawking radiation.
Yeah.
And because that radiation is purely thermal and depends only on mass, The radiation they emit is
Identical.
And eventually they both evaporate completely, leaving behind two identical clouds of warm, random radiation.
And there is no way, even in principle, to look at that final radiation and tell which one came from the neutrons and which one came from the books.
The history is erased. The unique, pure initial state has been transformed into a generic, mixed state of thermal garbage. That is a flagrant violation of unitarity. Information has been destroyed.
And that, right there, is the bomb that Hawking dropped on physics. For him, a relativist, it was just a strange consequence of the singularity, a place where the laws of physics break anyway.
But for the quantum physicists, like Susskind, it was an apocalypse. It meant the universe was fundamentally not deterministic. The past was lost forever.
So this wasn't just some academic debate. This was a fight for the soul of physics, and it got very personal very quickly.
It really did. The first major confrontation, where the battle lines were really drawn, happened in 1981. And the setting was, well, it was bizarre.
Not some hallowed university hall.
Right, not even close. It was in the attic of a San Francisco mansion that belonged to Werner Erhard.
Werner Erhard, the guy who created the AS self-help movement.
The very same. Apparently, he was a huge physics enthusiast and would host these super exclusive quantum gravity conferences for the world's top minds in his attic.
You can't make this stuff up, so you have Hawking, Susskind, Gerard Tuttle, all these geniuses crammed into a guru's attic.
And Hawking gets up and lays out the mathematical case for information loss. He uses this tool called the S-matrix to show, step by step, how a pure state becomes a mixed state.
And the reaction in the room was electric.
Oh yeah. Susskind later described looking at two faces. He saw Gerard Hooft with this intense, worried, furrowed frown, trying to find a flaw in the logic. And then he looked at Hawking, who had this little amused smile, like he was enjoying dropping this intellectual bomb on all of them.
Susskind knew right away this was a crisis. They all tried to argue with Hawking, but his argument was powerful because it was based on physics they all trusted. It was a semi-classical calculation.
Right. It used standard quantum field theory on the background of a classical spacetime, which seemed like a perfectly reasonable approximation. The paradox was robust.
And this really highlights the philosophical divide between the key players.
Absolutely. You had Hawking, the pure relativist. He trusted Einstein's equations. If they led to a singularity where physics breaks and information is lost, so be it. That's what the math says.
Then you had Kip Thorne, who was sort of the conservative relativist. He didn't want information to be lost, but his absolute top priority was preserving the equivalence principle.
Einstein's happiest thought.
The idea that gravity is indistinguishable from acceleration. And for a black hole, that means the experience of falling across the event horizon should be completely unremarkable, smooth sailing. No drama, as they called it.
For Thorne, any solution that put some weird physics at the horizon was a non-starter. That was a worse crime than losing information.
And then you have Susskind, the quantum mechanic, through and through.
For him, it was the other way around. Information conservation unitarity was the one non-negotiable law. He was willing to break the smooth geometry of space-time to do whatever it took to save it.
The war of ideas simmered for years, until 1997, when it was finally formalized in a very public, very famous way.
The Thorne-Hawking-Preskill wager. Signed at Caltech, it was a proper, high-stakes scientific bet.
So on one team, you have Hawking and Thorne arguing that information is truly lost.
Team information loss. And on the other, you had John Preskill, a Caltech particle physicist representing team information preservation.
And the terms of the bet were incredibly precise.
They were. Hawking and Thorne bet that information swallowed by a black hole is forever hidden. It never comes out. Preskill bet that a mechanism for the information to be released must and will be found.
And the prize, it wasn't money.
It was perfect. The winner would receive an encyclopedia of their choice.
An encyclopedia from which information can be retrieved at will.
The symbolism is just fantastic. The whole fight was about whether information could be retrieved from the ultimate cosmic dictionary, and the prize was a literal book of information.
So with the bet made, the pressure was on for Susskind and the preservationists. They had to come up with an actual physical mechanism.
And the problem seemed impossible. How can information get out if general relativity says nothing, absolutely nothing, can escape the event horizon? The information had to be in two places at once, inside the hole and also radiating away outside.
It's a flat contradiction, so how do they even start to approach it?
Susskind's big insight was to go back to the equivalence principle, the very thing Thorne was trying to protect, and look at it from different points of view. The observer's point of view.
No drama rule.
Right. If you're an observer freely falling into a black hole, You shouldn't feel a thing as you cross the horizon. It should just feel like empty space.
So for that infalling person, the reality they experience is that the object and its information passes right through the horizon and heads for the singularity.
That's the interior reality. But now consider an external observer, someone hovering safely far away, watching with the super telescope.
What do they see?
Because of the extreme time dilation near the horizon, they see something completely different. They see the falling object slow down as it approaches the edge. It gets dimmer, redshifted.
And it seems to get flattened and spread out over the surface of the horizon.
And its information gets scrambled and then radiated back out over time as Hawking radiation. From the outside observer's point of view, the object never actually crosses the horizon. Its information is returned to the universe.
Wait, hold on. So for the person falling in, the information is inside. For the person watching, the information is outside. How can both be true? That breaks our sense of a single, objective reality.
It absolutely does. And this was Suskind's radical proposal. He said, what if both are true? What if reality itself is observer-dependent? He called it black hole complementarity.
Like wave-particle duality in quantum mechanics, a photon is a wave or a particle depending on how you measure it.
Exactly. Here the information is inside or outside, depending on who is asking. He, along with Thorlacius and Uglum, laid out the postulates in 1993.
Let's walk through them. They were trying to build a new set of rules to save physics.
Postulate 1 was the quantum demand. The whole process from formation to evaporation is unitary. Information is preserved, full stop.
Okay, that saves quantum mechanics.
Postulate 2 was the relativity demand. Far from the black hole, physics works just like Einstein said it would. No weirdness in the outside world.
Postulate 3 was the thermodynamic one.
Right. The black hole has a finite entropy proportional to its area, as Bekenstein said. It's a normal quantum system.
And the final one, postulate 4, was the no drama rule. The equivalence principle holds true for any infalling observer.
Right, so to make all this work for the external observer, they needed a physical place for the information to live. They introduced the idea of the stretched horizon.
This isn't the true mathematical event horizon.
No, it's a physical membrane, a hot layer of something that exists about 1 Planck length, the tiniest possible distance above the true horizon.
And this membrane is what the outside world interacts with.
For the external observer, yes. To them, this stretched horizon is a real physical thing. It's hot, it has electrical conductivity, viscosity. It's a surface. When stuff falls in, it doesn't cross the horizon, it hits this membrane.
And it gets smeared out, scrambled, and its information is then re-radiated as Hawking radiation.
So from the outside, the information never went in. It stayed on the surface and came back out. Unitarity is saved.
But for the person falling in,
the membrane doesn't exist. They sail right through it, experiencing nothing, no drama. They carry a copy of the information inside with them.
So now we have the information in 2 places. Outside, on the scrambled membrane, and inside with the falling astronaut. Doesn't that violate the no cloning theorem?
Ah, the crucial objection. The no cloning theorem is a fundamental law of quantum mechanics. You cannot make a perfect copy of an unknown quantum state. If complementarity does that, it's dead on arrival.
So how did they get around it?
With a very clever, and some would say slippery, argument. They argued that no single observer can ever confirm that both copies exist at the same time.
Why not?
The time scales. For an outside observer to collect all the Hawking radiation and decode the information from it would take an absurdly long time. Billions, maybe trillions of years.
So, by the time you've confirmed the outside copy exists, the inside copy has long since hit the singularity and been destroyed.
Exactly. And if you try to jump in to check the inside copy, you can't send a signal back out to tell anyone. There is no experiment you could possibly perform that would allow you to see both the original and the clone in the same measurement.
So the paradox is avoided operationally. It's not that cloning doesn't happen, it's that it's physically impossible to ever prove it happened.
That was the resolution. And it was the dominant paradigm for almost 20 years. It held the peace.
And this idea, complementarity, led to something even bigger, didn't it? It wasn't just about black holes anymore.
That's right. The core idea of complementarity is that all the information about a 3D volume, the inside of the black hole, is actually encoded on its 2D surface, the stretched horizon.
So Susskind and Hoof started wondering, what if that's a universal rule?
What if that's true for everything? This became the holographic principle.
The universe as a hologram.
The idea is that the reality we experience in 3 dimensions, with gravity, stars, planets, us, might just be a projection, an illusion of a sort. The real fundamental physics is happening on a distant two-dimensional boundary surface that encodes all the data.
That is just a mind-bending concept. It completely upends our intuition about space.
It does. It suggests that the third dimension is an emergent property. And the evidence for it came from Bekenstein's original entropy calculation. The maximum information you can cram into a region of space isn't proportional to its volume, as you expect. It's proportional to its surface area.
The boundary area, so the information storage capacity is holographic.
It seems to be. But for a long time, this was a powerful but speculative idea. Then, in 1997, came the smoking gun, the hard mathematical evidence the preservationists needed.
The ATA-CFT correspondence.
Discovered by Juan Maldacena. It's probably the most important theoretical discovery of the last 30 years.
It's a bit of a mouthful. Can you break down what it means?
Maldacena found a mathematical duality, a perfect dictionary, that translates between two completely different-looking theories.
Okay.
On one side of the dictionary, you have a theory of quantum gravity, like string theory, living in a specific kind of five-dimensional universe called anti-de Sitter space, or ADS. It's a universe with a boundary.
And on the other side?
On the other side, you have a four-dimensional quantum field theory, a theory without gravity that lives only on the boundary of that 5D space. This is the conformal field theory, or CFT.
So a theory of gravity in 5 dimensions is mathematically identical to a normal quantum theory without gravity in 4 dimensions.
It's a perfect equivalence. Every question you can ask in the gravity theory has a corresponding translatable question in the boundary theory, and they always give the same answer.
And here's the killer punch for the black hole war.
The boundary theory, the CFT, is a standard quantum field theory. By its very construction, it is unitary. It conserves information. It has to.
And since the 5D gravity theory is just a different description of the same physics,
the gravity theory must also be unitary. It must preserve information. Information loss in a black hole within this framework is mathematically impossible.
This was the proof they needed. The tide of the war turned decisively.
It was a monumental victory for the quantum camp, and it led directly to the moment everyone was waiting for, the concession.
In Dublin, 2004, Stephen Hawking officially surrenders.
He does. In a huge moment for science, he stood up at a conference and announced he'd been wrong.
What was his reasoning for the change of heart?
He had done a new, more complex calculation using something called Euclidean path integrals. It's a way of summing up all possible histories of the universe. He found that if you include histories where a black hole never truly forms, those possibilities ensure that the final outcome is unitary.
So information is preserved, but he added a little caveat, didn't he?
He did. He said, yes, the information gets out, but it's so mangled and scrambled in the radiation that for all practical purposes, it's lost. You could never decode it. He also argued that a true, permanent event horizon might never actually form, only a temporary, apparent horizon.
And with that, the bet was settled. John Preskill got his prize.
He did. Total baseball, the ultimate baseball encyclopedia. And Hawking, with his classic wit, joked that maybe he should have just given Preskill the ashes of the encyclopedia to represent the scrambled state of the returned information.
A perfect ending,
Yeah.
Except it wasn't the end. Because one person refused to sign off on the concession.
Kip Thorne, the conservative relativist. He held out.
Why? It seemed like the case was closed.
He was still deeply bothered by the lack of a clear physical mechanism. He said, okay, ATA-CFT is great, but it's a model in a toy universe, not ours. And Hawking's path integrals are mathematically abstract. He wanted to know, physically, how does the information get through the event horizon without violating the no-drama rule? He felt that question was still unanswered.
And it turns out his skepticism was prescient, because the peace achieved by complementarity was about to be shattered.
Completely shattered. In 2012, a paper dropped that ignited the second phase of the black hole war. It's known simply as the AMPS paper for the author's initials.
Almeri, Marolf, Polchinski, and Sully, and they found a fatal flaw in black hole complementarity.
They did. They showed that you couldn't have it all. You couldn't satisfy all 4 of Suskind's postulates at the same time. You had to make a choice. And the problem came down to a core principle of quantum information: the monogamy of entanglement.
The monogamy of entanglement, what is that?
It's a very strict quantum rule. It says that a quantum particle can be maximally entangled with one other particle, and one only. Entanglement is a monogamous relationship. If particle A is fully entangled with particle B, it can't also be fully entangled with particle C.
It can't be loyal to 2 partners at once.
Exactly. Now, AMPS applied this rule to an old evaporating black hole. Think about a particle of Hawking radiation that has just been created at the horizon. Let's call it particle R for radiation. According to complementarity, particle R has to satisfy two contradictory entanglement conditions.
The first one is to save unitarity, right? To preserve information.
Yes. For the information of the original star to be recoverable, this new particle R must be entangled with all the radiation that came out before it, the early radiation, E. That's how the story of the star gets encoded in the full cloud of radiation. So R must be entangled with E.
Okay, that's requirement A. What's requirement B?
Requirement B is to save the no-drama horizon, the equivalence principle. For the space-time at the horizon to look like smooth, empty vacuum to a falling observer, the particle R must be maximally entangled with its partner particle, P, the one that fell into the black hole.
Ah, I see the problem.
There it is. The particle R has to be fully entangled with the early radiation E outside the hole, and at the same time be fully entangled with its partner P inside the hole.
It's trying to be loyal to two different independent systems. It violates the monogamy of entanglement.
It's an impossible contradiction. AMPS showed you have to choose. You either preserve unitarity, A, or you preserve the smooth horizon, B. You can't have both.
So what did they argue we should give up?
Well, by 2012, the evidence for unitarity from AD-SCFT was so strong that most physicists believed it had to be saved at all costs. So AMPS said, we must keep requirement A.
Which means you have to sacrifice requirement B. You have to break the entanglement between the outgoing particle and its infalling partner.
And what happens when you violently sever a maximal entanglement bond in quantum field theory?
It releases a huge amount of energy.
A catastrophic amount of energy.
Blah.
AMPS calculated that if you do this for every single particle of Hawking radiation being created, you create a searingly hot curtain of high-energy particles right at the event horizon.
A wall of fire. The firewall.
The firewall. The result is that anyone trying to fall into the black hole wouldn't experience no drama. They would be instantly incinerated on contact.
That is the ultimate violation of the equivalence principle. The smooth, gentle horizon of Einstein's theory is replaced by a physical, violent wall of death.
It put the war right back to square one. Kip Thorne's original fear was realized. The choice was stark. Either information is lost, or general relativity is wrong at the event horizon.
The firewall paradox was a huge crisis. It meant the easy compromise of complementarity was wrong, and something much deeper and stranger had to be going on with space-time itself.
Exactly. The focus shifted. The problem wasn't just about information anymore. It was about the very fabric of geometry. And this led Maldacena and Susskind in 2013 to propose a radical new truce. A very simple, very strange equation. ER-EPR.
Okay, let's break that one down. EPR is quantum entanglement.
Right, Einstein-Podolsky-Rosen, the spooky action at a distance that connects two particles no matter how far apart they are.
And DR.
Einstein-Rosen bridges. That's the technical term for a wormhole, a geometric tunnel through spacetime.
So the conjecture is wormholes are entanglement.
Or entanglement is wormholes. They are two different descriptions of the same physical reality. The idea is that any two entangled particles are physically connected by a microscopic wormhole. Space-time geometry itself is built from quantum entanglement.
So that spooky quantum connection is actually a physical bridge in the geometry of the universe.
That's the proposal. And if you apply this to the black hole, it could solve the firewall paradox. The late Hawking radiation isn't an independent system from the black hole's interior.
Because it's connected to it by a web of these tiny wormholes.
Right. The interior of the black hole, in this view, is literally constructed out of the entanglement it has with the radiation that has already escaped. They are two separate things, so the monogamy rule doesn't apply in the same way.
The interior space is an emergent property of the exterior quantum state.
It's a way of giving the equivalence principle a quantum mechanical foundation. The reason the horizon is smooth is because breaking the entanglement to create a firewall would be the same as tearing apart the very space-time of the black hole's interior.
That's a profound idea. And it seems to be supported by the latest work in the field, this concept of entanglement islands.
Yes, this is the frontier right now. Around 2019, researchers using these incredibly complex path integral calculations, same kind of math Hawking used for his concession, made a breakthrough.
What did they find?
They found that when you calculate the true entropy of the Hawking radiation late in the black hole's life, the calculation only gives the right unitary answer if you include a portion of the black hole's deep interior, a region they call the island, as being part of the radiation system.
So a piece of the geometry that we thought was trapped inside is, from an information theory perspective, actually part of the system that got out.
It's mathematically part of the exterior now. This provides a mechanism for the information to be accounted for in the radiation, ensuring unitarity is preserved without needing to invoke a violent firewall at the horizon.
And these calculations correctly reproduce the Page curve, right?
They do. The Page curve is the theoretical graph of what the black hole's entropy should look like over time if information is conserved. It goes up, and then it goes back down to zero. Hawking's original calculation just went up and stayed there. The island calculations get the downward slope right.
It really feels like a synthesis. The war forced physics to this point where space and time are no longer fundamental, but are emergent properties of these deeper quantum information rules.
That really is the takeaway. The war started as a simple bet over an encyclopedia and ended up completely rewriting our understanding of reality.
So let's try to sum up this deep dive. We've seen how this conflict, this black hole war, was this crucible that forced physicists to grapple with the collision of their two greatest theories.
And out of that crucible came a clear victor, the principle of information conservation. Unitarity won. But the price of that victory was accepting that reality is far, far stranger than we ever imagined.
It led directly to the holographic principle and this newer idea that space-time itself is woven from the threads of quantum entanglement.
The black hole went from being this symbol of ultimate destruction to being seen as the ultimate quantum computer, a device that takes in information, scrambles it on its surface, and slowly returns it to the universe.
But even with all these breakthroughs, at SCFT, ER, entanglement islands, the central mystery isn't fully solved, is it?
That's the crucial point. We now have overwhelming mathematical evidence that information is saved, but the question that Kip Thorne asked all those years ago still lingers. How physically does the information get out without creating a firewall? The answer seems to be non-local effects, these wormholes, these islands, but what that looks like to an astronaut falling in is still the subject of intense debate.
The legacy of the war is this new picture of the universe, where the information of a volume is written on its boundary, where the inside of a black hole is quantum mechanically linked to radiation trillions of miles away.
Which leaves us with a final, really provocative thought for you to consider, building on this idea of ER-EPR. If space-time is literally built from entanglement, what does that mean for our everyday reality?
What's it imply?
Well, think about two particles right here in this room. They have some entanglement, some quantum connection. The theory suggests there's a tiny wormhole between them. If you fully separate them, fully disentangle them, are you actively tearing a little piece of space-time? And if you could control all the entanglement in a region, could you literally build or dissolve the geometry of space itself? The war may be over, but the exploration of the strange new reality it uncovered has only just begun.